Hi, this is Dr. Anthony Revis, and this is SVSU, General Chemistry 111, Chapter 4, Lecture 1. That's Lecture 1 of Chapter 4, entitled Stoichiometry and Chemical Reactions. We'll cover writing and balancing chemical equations, classification of chemical reactions, reaction stoichiometry. We will also look at reaction yields and quantitative chemical analysis. These topics will be covered, however, they might not be covered in this order. Let's get started with the discussion on chemical equations. So how do you read a chemical equation, and what is a chemical equation? A process in which one or more substances is changed into one or more new substances is a chemical reaction. That reaction is expressed in a chemical equation. So essentially, a chemical equation is how we write chemical reactions, how we use the symbols of chemistry to write a chemical equation. And when you think about a chemical equation, it is a good idea to think about it in terms of math, because a chemical equation will be mathematically balanced as well as will not disobey the laws of conservation of matter. Okay? The substances undergoing a chemical reaction are called the reactants. The left side equation are the reactants. So you have the reactants on the left side equation. On the right side, what's being formed are called the products. And so we write the reactants on the left and the products on the right. Regardless of how many there are, if they're located on the left side, they're reactants. Regardless of how many are formed, they are called products. Here's an example. Magnesium plus oxygen gives magnesium oxide. A balanced equation, which you will learn how to do, involves adding a coefficient of 2 in front of magnesium so that we have the same number of atoms of magnesium react with oxygen. Oxygen is diatomic, so it's O2, gives 2 molecules of magnesium oxide. And the coefficients are added to balance the equation. Again, you will learn how to do that. So, again, we have 2 atoms of magnesium, 1 atom of oxygen, 2 moles of magnesium to give 2 atoms of magnesium oxide. There are other notations that you have to be aware of when it comes to a chemical equation. The physical state of reactants and products are often indicated with a parenthetical abbreviation following the formula. For example, G represents gas, L liquid, S solid, and AQ for aqueous. There are other symbols or notations that are used as well. Delta stands for heat. Arrows stand for yield or direction of the flow of reactants to products. And double-headed arrows mean equilibrium, meaning there's a free flow in both directions. We show you an example here of sodium plus water to give sodium hydroxide plus hydrogen gas with the appropriate notation. We also want to be aware of something that's called heat of reaction. Heat of reaction values may also be written in the equation. Exothermic reaction values are written on the right side of the equation, and endothermic values are written on the left. Compound writing is done with the electropositive element written first and the electronegative element written second. This is a convention for writing compounds. In other words, the convention for writing compounds is to write the electropositive element first, followed by the electronegative element. For example, in the case of water, H2O, hydrogen's electropositive, oxygen's electronegative. In the case of sodium hydroxide, sodium's electropositive, OH is electronegative. That is the convention for writing chemical compounds. A chemical reaction occurs by a balancing of the atoms. In other words, the atoms on the left side will be balanced with the atoms on the right side of the chemical equation. Be reminded that you cannot destroy nor create matter, but you can transform it. But the mass of that matter will remain the same. So, what's a balanced equation? A balanced equation is the process of adding coefficients to a reaction equation such that all atoms, which are elements, of each compound on both sides of the reaction equation, both sides of the arrow, is equal to that on the other side of the equation. Stoichiometry is the determination of the quantitative relationship between two or more substances based on the numeric ratios in the chemical reaction and processes. The stoichiometry of an equation is critical. When we balance the equations, we add small whole numbers in front of the atoms to balance them out. So those numbers in front of the equation, that's how we read stoichiometry. And we adjust that stoichiometry until the equation is balanced. Now, the equation actually knows it's balanced when it's carried out. Coefficients then are used to determine the stoichiometry of the compounds in the balanced equation. They represent the molar ratio of the compounds in the balanced equation. The coefficient in a balanced equation represents the molar quantities in the compound and are used as conversion factors for chemical transformation. We look at the coefficients, we look at the stoichiometry, we look at the balanced equation. And in carrying out chemical reactions or solving problems in chemistry, the very first thing that you should do when you have an equation is check to see that it's balanced. Do not assume that it's balanced. General chemistry professors will often leave the equations unbalanced as a way of checking to see whether or not you've noticed it or not. So be aware of that you must balance the chemical equations. We show you an example here with iron 3 oxide. We have plus carbon to give iron plus carbon dioxide. We add coefficients 2, 3, 4, and 3 in front of the compounds to balance out the atom count on the left and on the right. This process is known as carbothermic reduction. So essentially, iron 3 oxide is reduced to iron plus carbon dioxide, in which the carbon has been oxidized. You will learn more about oxidation and reduction in this chapter. So let's practice balancing some equations. Now, I am going to walk you through some steps to do this. However, there are no magical steps, no magical routes to balancing equations. And in fact, you are not required to follow my method of balancing the equations. If you can intuitively do this without having to write everything down, then that's perfectly okay. In my lectures, I do not ask you how you balance the equation. I simply expect you to balance the equation. Some of you will find this to be very, very easy. Others will find it to be frustrating. Those who find it to be easy will have some intuitive sense about what just makes sense for the math. Others will struggle with the math. The best way to get good at this is to simply practice and find your own unique ways of thinking about your atom count. In the examples I'm going to show you, we have written out all the elements to help you see how we counted them. Typically, I simply go to the board and start the balancing process. and you have to use some common math rules in order to do that. Okay? So again, let me repeat. You are not required to prove how you balance an equation. If you have your own quirky way of balancing an equation, that's perfectly okay, as long as it does not violate the rules of math when you do it. Okay? So let's do it here by counting the atoms to show you what it looks like, or what the thought process looks like. So we're going to write a balanced equation for the combustion of methane. The complete combustion of methane generates carbon dioxide and water in the presence of oxygen. So if we were to take a balanced count, we would find this initial count. 1 to 1 carbon atom is balanced, 4 to 2 carbon atoms is not balanced, 2 oxygen, and 3 is not balanced. Now, it's important to note that as you make adjustments to balance the equation, you will have to recount. Seeing that carbon is balanced does not mean this is the final value. Let me reiterate it. Just because it starts out balanced does not mean the stoichiometry C it will be or is the final stoichiometry for it. It's okay to change the coefficients until it's completely balanced. Do not assume because it starts out with one species balanced that stoichiometry will remain the same. That is a mistake that many students make in freshman chemistry. They will see an atom balanced and they refuse to change it because they don't want to disturb the balance. It's a balancing back and forth until you obtain a final balanced equation. So let's balance the equation. Since the carbons are currently balanced, I proceed to balancing the hydrogens. Since there are 4 hydrogens on the left side and only 2 hydrogens on the right side, I add a coefficient of 2 in front of the water, and that increases the number of hydrogens on the right side to 4. So now when I count, I have 1 carbon on the left, 1 carbon on the right. 4 hydrogens on the left, and now I have 4 hydrogens on the right. However, I still only have 2 oxygens on the left and 4 oxygens on the right. And so in order to balance the oxygens, I add a coefficient of 2 in front of the oxygen on the left, and it gives me a balanced equation. Now, I want to warn you that listening to me talk through this can sometimes be more painful than simply looking at it and doing it. If you can intuitively do this and understand the math, then go right ahead and simply balance the equation. Do not feel pressured to adjust to one of the methods you read in the textbook or that I use. If you have a way of balancing an equation, just balance it. Okay? Let's practice balancing another equation. In this reaction, we have sodium phosphate reacted with magnesium chloride. The reaction is carried out, and we look at the species on each side. Now, where we have polyatomics, it is often convenient to balance the complete polyatomic. However, you can write out each element and balance it. But if the polyatomics don't change from left to right, it is easier, or tends to be easier, to simply balance them based upon the polyatomics, which is what we're going to do in this example. We wrote out the ions, although it is not required to write the charges with these ions. We do this simply to show you what the ions look like. But to balance the equation, you don't need the ions. You will discover later, when we're doing ionic chemistry, how to use these ions and how to do balance regarding ionics. But for simple, straightforward balancing equations, we don't have to consider the ionic charge. So let's take a look at this one again. We have the sodium phosphate with mag chloride, giving us magnesium phosphate and sodium chloride. We have these elements and ions. The initial inspection shows that the sodium is not balanced on the left and right. The phosphate is not balanced. The magnesium is not balanced. And the chloride is not balanced. And again, because we have the same polyatomics on both sides, we're going to balance this based upon polyatomics instead of the individual atoms of phosphorus and oxygen. You can start to balance this anywhere, but we choose to balance starting with the phosphates. One reason we do that is because if we look at its composition, that particular compound appears to be more complex. So kind of a general rule of thumb is to try to balance the complex polyatomics first, or the more complex elements or atoms first. But again, there is no magic to doing this. Find your own way to balance it. But we're going to take a look at the polyatomics first when we balance. So we look at polyatomic phosphate. We balance it by adding a 2. That puts a 2 on both sides of the equation. And then we move on to balancing the magnesiums here. And we know that we have 3 magnesium on the right side. So we've added a 3 in front of the mag chloride on the left side. That balances out them. And that increases the number of chlorines now to 6. So to balance out the chlorines, we add a 6 to the sodium chloride side of the reaction. And we note that when we do that, that adds 6 sodiums also. And if we go back to the left side of the equation, we notice that we had 2 times 3 sodiums there, therefore it's balanced. Balancing equation multiplies the coefficient times the subscript. Keep that in mind. It's the coefficient times the subscript. Make sure you follow the rules of math when it comes to parentheses. For example, in the case of the polyatomic phosphate that's combined with magnesium, we have 2 times 4 oxygens and we have 2 times 1 phosphorus. So you want to make sure you watch the parentheses, watch the subscripts, and watch the coefficient. They're all important when it comes to balancing equations. So that's it for how we balance equations using coefficients. Let's move on now to using these coefficients to carry out chemical processes. One of the relationships that we find once we have a balanced equation is that the molar ratios of the elements and compounds, substances, or species in the balanced equation can now be determined. And those mole-to-mole ratios will allow us to have a mole-to-mole conversion factor. Why is that important? In a chemical reaction, the materials on the left side are being transformed into new species or different species on the right side. That interconversion is based upon its mole-to-mole ratio, its atom-to-atom ratio. Although we use grams to carry out chemical reactions, it is the molar ratio that determines the output. So, when we have a balanced equation, we examine those mole-to-mole conversion factors, and that mole-to-mole conversion factor is a ratio of the moles of the two substances in a chemical equation. So what does that mean? Take a look at this balanced equation between iron and sulfur to give iron 3 sulfide. And it's called iron 3 sulfide because iron is a transition element and it's combined with a nonmetal. And the rules for naming these is to name the cation followed by the anion with IDE, and to use a Roman numeral to describe the oxidation state, the charge on the metal. You will learn this as we go. So we have iron plus sulfur to give iron 3 sulfide. So we can examine these ratios. The ratio of iron and sulfur is 2 mole of iron for every 3 mole of sulfur, but you can invert that to be 3 mole sulfur to 2 mole iron. The ratio of iron to iron sulfide is 2 irons per every 1 mole of iron 3 sulfide, and you can invert that molar ratio as well. And then there's the ratio of sulfur to iron 3 sulfide, 3 to 1 or 1 to 3. Keep in mind, you will know which ratio to use based upon the given and what you're looking for. The very first thing to do in doing these conversions is to write your given. The units in the given will dictate the units in the first conversion factor. You can always get the first conversion factor right if you write the given first. So let's do some calculation using these molar ratios. In a chemical reaction of iron and sulfur, how many moles of sulfur are needed to react with 1.42 mole of iron? We have the balance equation, and that is the very first step in any of these reactions is to write the balance equation. So we've balanced the equation, we've checked the balance equation. And now we take our given. Our given is 1.42 mole of iron. We do a cross-bar dimensional analysis where moles go on the bottom because our given dictates the first conversion factor have mole on the bottom. And we can go mole to mole because that is allowed in chemistry. So we go mole of iron to mole of sulfur. And we know that from the balance equation. And we cancel out mathematically. And we're left with 2.13. It results in 2.13 moles of sulfur. 3 sig figs in the beginning, 3 sig figs at the end. We show you the conversion factors here where 2 moles of iron equals 3 moles of sulfur, and you can read that either way. Let's take another example. Propane gas, C3H8, is a fuel used for camp stoves, soldering torches, and special equipped automobiles, racing vehicles. It reacts with oxygen to produce carbon dioxide, water, and energy. In fact, it is an exothermic reaction. We know this because the energy is released and is written on the right side of the equation. So here's the question. How many moles of carbon dioxide can be produced when 2.25 mole of propane reacts? We write the balance equation, we inspect the equation, we observe that it is balanced. We write the given of 2.25 moles of propane. We do a cross hash bar 1 mole on the bottom because our given has moles in it. We then convert moles of propane to moles of CO2, and we write absolutely all the important features of the units because it is a unit analysis. Then we calculate the numbers through, and we obtain 6.75 moles of carbon dioxide with 3 sig figs because our given has 3 sig figs. We show you the molar ratios that might be useful in carrying out this. Okay? So, you don't have to write out all the molar ratios. Write the ones that matter for the transformation you're carrying out. And you'll know which one matter for the transformation based upon the given and what you're after. Now, we've looked at how to examine mole-to-mole ratios. We looked at how to calculate moles of reactant. We've looked at how to calculate moles of product. Let's take a look now at how to take grams of reactant to grams of product. So, here's the problem. How many grams of carbon dioxide can be produced when 54.6 grams of ethylene is burned? So, we have ethylene, and we have 54.6 grams, and we want to know how much CO2 is produced. CO2 is an indicator that this is complete combustion. Incomplete combustion involves carbon monoxide. So we set up a dimensional analysis as we've done before. We write the given, cross hash bar, 26.04 gram on the bottom, mole to the top, now cross hash bar, mole on the bottom to moles of CO2 on the top, then cross hash bar, 1 mole of CO2 to grams of CO2. We punch the numbers through, and our answer has 3 sig figs because our starting reagent, our given, had 3 sig figs. So that's how you carry out these inner conversions between moles to grams, grams to moles, and grams to grams. Here we show you a full map of what that looks like. We're not requiring you to memorize the map. For some, this is helpful to help them understand the concepts of where they're going. But the key to carrying out any of these is to write your given first and trust the first step to be a conversion factor that involves the same units in the given written on the bottom of that first conversion factor. That is absolutely the best way to start these processes. Now, we've talked about carrying out these reactions, but we haven't talked about the names of these reactions and what type of reactions we're carrying out. We've mentioned some along the way to start to introduce the concept so that you're aware of it. But now let's take a closer look at those reactions. Let's look at the types of reactions in chemistry. And we will discuss 5 of those reactions. They're classified either as combination, decomposition, single replacement, or you'll hear the term single displacement. And in fact, occasionally you will hear me use it interchangeably. So it'll be single replacement or single displacement, double replacement or double displacement, and combustion. We show you those here on the slide as a summary. Okay, we will go into each of these in more detail. But we have 5 reactions that you will want to memorize, and we're going to show you what they look like by showing you a diagram and showing you some exact examples, and hopefully we'll give you some pretty good hints on how to identify them as well. In a combination reaction, 2 or more elements or compounds form one product. 2 or more simple compounds combine to form one product. So a combination is straightforward. 2 things go to 1. That is the bottom line. It's a combo. Got it? It is that straightforward. Don't complicate it beyond that. 2 going to 1, 2 substances on the left, going to 1 substance on the right. Combo. Combination. We show you some examples here of where magnesium combines with oxygen. And we show you also an example where nitrogen combines with hydrogen. Both of these reactions are combination reactions, and that's because they give a single compound. Note that we bring your attention to the states of matter. You want to start paying attention to the states of matter because it will become more and more important as you carry out these reactions. And it will become particularly important as we get to ionic reactions and writing ionic equations. Decomposition reaction really is the opposite of a combo. This involves the reactant split into 2 or more simpler species. Okay? So you'll go from a single material to 2 or more materials. More times than not, in Gen Chem, it's 1 going to 2. So it's just the opposite of the combination, the combo. You have the combo, then you have the decomp. So the decomp will be 1 going to 2. And keep in mind, the reactions must be balanced. That is important. Balancing equation must be considered in any chemical reactions. So as you continue in Gen Chem, balancing equation is a critical step and a critical consideration in carrying out your chemistry both in lectures and in lab. So we have the balanced equation here with these materials, and it's 1 going to 2. Now, a single replacement or single displacement, okay, involves a reaction in which an uncombined element replaces an element in a compound. In other words, you'll start with an element, and that element will be substituted into the compound, and the element that's in the compound will be kicked out. Okay? So that's why it's a replacement or a displacement. So you have one element comes out and kicks out another element. So you look for an exchange, if you will, of the element. That's what's going to happen. But it's only single. Keep that in mind. One element comes in and one element comes out. That's critical. That's important. So we show you an example here is zinc with hydrochloric acid. Then we show you an example of iron with copper 2 sulfate to give the corresponding iron 2 sulfate and copper 0. And in the case of zinc, you get the zinc 2 chloride and hydrogen. So that's a single, but what about a double? In a double displacement, 2 elements in the reaction exchange places. So the reactants exchange completely. Okay? You go from an ABCD to an ADCB. So you get 2 species will change places. That's going to be a double replacement or a double displacement. We show you an example here of silver nitrate, silver in the one state, nitrate with sodium chloride, going to give silver in the one state with chloride and sodium nitrate. And then we have sodium hydroxide and HCl. And that was a classical example. Acid-base reactions are the classics for this. And in fact, precipitation reactions occur as well. So these types of reactions involve a double, 2 doubles going to 2 new doubles. You got it? All right. So let's practice by identifying the types of reactions shown here. In the case of the first one, we notice that it is a combination reaction with barium and nitrogen. So we go from 2 to 1. That's a combo. By the way, combo is also referred to in some textbooks as synthesis. So be aware of that. So you want to be ready to deal with synthesis or combo because occasionally Chem professors will use those 2 terms interchangeably. Okay, and it's often depending on which textbook they're using at the time. So the term synthesis also means combo. The second one is a single replacement or single displacement because we have silver replacing hydrogen in the hydrogen sulfide. Then we have a double displacement. We go from silicon dioxide and hydrogen fluoride to silicon tetrafluoride and water is a double displacement or a double replacement. And then we have the potassium carbonate going to potassium oxide plus carbon dioxide, which is a decomposition. That brings us to the combustion reaction. In a combustion reaction, a carbon-containing compound, a fuel, which comes from fossil fuels, oil, burns in oxygen from the air to produce carbon dioxide for complete combustion plus water and heat or flame. We get energy from it. So here we show you the complete combustion reaction, which produces carbon dioxide and is balanced. We have 1 molecule, 1 mole of methane plus 2 molecules, 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water. That's for complete combustion, which is what you prefer, particularly if this is in your car engine, where you want to produce carbon dioxide and not carbon monoxide, which is a pollutant. However, in some instances, incomplete combustion does occur. In that case, you get a completely different balanced equation. Carbon monoxide happens oftentimes around campfires or burning wood for heat. So this is what a combustion reaction looks like. And so with any of these reactions, we can use them to carry out chemical processes that help us to understand the reaction sequence. How do reactions occur in the laboratory, in nature, and we can understand that by using mole-to-mole ratios, converting moles to grams. We can convert grams to grams, but we must go through it in a conversion factor of moles to mole. We can either have a reaction that is characterized as combination reaction, in which 2 species produce 1 new species. It can be characterized as decomposition, where a single species produces 2 new species. We can have single replacement, or often called single displacement in some textbooks, where you have one material displacing one element to produce a new material with a new single species. You can also have double displacement, where both reactants react to give you 2 new species. And then you can have combustion, where combustion burns hydrocarbons, combusts hydrocarbons to produce CO2 and water. If it's complete combustion, incomplete combustion, carbon monoxide. And that completes Lecture 1 of Chapter 4. Lecture 1 of Chapter 4, Stoichiometry and Chemical Reactions.